Hello my dear students, welcome back to my channel. In today's lecture, we will be discussing some problems related to elasticity. So let's start with today's class with this first question, that is, find out the shift in position B, C and D in this diagram. Okay, they have given you the Young's modulus of the AB part. Okay, this rod is made of three materials. Part AB is first material, part BC is the second material, and part CD is the third material. Okay, so YAB I have written it as Y1, YBC I have written it as Y2, and YCT I have written it as Y3. The length L1 of the first segment, L2 is of the second segment, and L3 is of the third segment. Okay, they've given you the values, but we will solve it in variables. They've given us the area of cross section also. So let the area of cross section be A, and let the mass of the block connected here is M. Okay, now because this rod is massless, so you will say that the tension at every point is same. Okay, so if the tension is same and the area of cross section is also same, that means the stress is same. If the stress is same, then for every cross section the strain is also same, right? And the tension at every point is how much? The tension at every point is mg. We have studied in Newton's law that for a massless rod, tension at every point has to be same, right? So now you know that Hooke's law states that stress is equal to y strain. That means F by A is equal to y delta L by L. So from this we will get delta L, that is the elongation, is equal to FL by AY. So the elongation is given by FL by AY. Now let us look at the first rod, this one. So what will be the elongation in this rod? The elongation in this rod will be delta L1 is equal to FL1 by AY1. Now what is the value of F? The value of F here is the tension. Okay, the deforming force here is the tension. Although stress is restoring force per unit area, but we will write the stress as deforming force per unit area because we are considering that the body is completely elastic. When the body is completely elastic, I have told you in the last class that the restoring force is equal to the deforming force. Okay, so the deforming force here is the tension, right? And tension is equal to mg at every point. So by Newton's law you will say that tension is equal to mg at every point. So the deforming force F or T is equal to mg. So here instead of F we will write mg, and instead of L I will write L1, and instead of Young's modulus I will write Y1. Okay, so this is the elongation of the part AB of the rod. Similarly, the elongation of the part BC of the rod will be equal to tension, again tension is mg, into length, length is L2, divided by area of cross section is same for all the segments, and the Young's modulus is Y2. Similarly, delta L3 will be equal to mg, again the tension, into length, the length is L3, area of cross section is A, and the Young's modulus is Y3. So this part, see, listen carefully now. This part has an elongation of delta L1. So that means this region, this BC, has come down by a distance delta L1. Similarly, this part has come down by delta L2 from here. Okay, but this region also came down by delta L1. So actually this part will come down by delta L1 plus delta L2. Similarly, this part, only this part elongated by delta L3, but this two part elongated by delta L1 and delta L2 respectively. So this part came down by delta L1 plus delta L2 plus delta L3. So we will write the elongation in part B. The elongation in part B will be equal to delta L1. So the descent, elongation means what? The descent, here it is going down, so descent. So descent of B is delta L1, okay, which is equal to this, and the descent of C is delta L1 plus delta L2 because it is going down along with this, as well as this part is also stretching. Okay, similarly this part, that is the end D, is coming down, or it is descending by delta L1 plus delta L2 plus delta L3. So the answer will be the shift in position B is delta L1, for C it is delta L1 plus delta L2, and for D it is delta L1 plus delta L2 plus delta L3. Now let us look at the next part. This is very, very important. Elongation of a rod under its own weight. So what will happen is, if a rod has mass, then it will elongate due to its own weight. Okay. So suppose this is a rod of length L and mass M. Okay. You know that whenever a rod has mass, then tension at every point is different. Okay. By Newton's law, if you remember, by Newton's law, we can calculate the tension at any point. So suppose you want to find the tension at this point, which is at a distance of x from the bottom. Then what you will do is, you will choose a system which has this point. Okay, we will choose a system which has this point where you want to find the tension. So if you draw this system, because this system is in equilibrium, that means the net force has to be 0. So here what we will do is, here we will write m by L into x into g. This is what? M by L into x into g. This is the force of gravity, and that is downwards. And this point is being pulled by this part. Okay, the tension is a pulling force. So at this point, the tension force due to this region is trying to pull it. Okay, so the tension is T, but because it is in equilibrium, then we can say that T is equal to m by L x. So from the bottom at a distance x, the tension is equal to m by L into x into g. So now, if the tension at every point is different, that means the stress is different. If the stress is different, that means the strain is different. If the strain is different, that means every point is elongating differently. Now, if every point is elongating differently, then what we have to do is, we have to take an element. Okay, so at a distance x from the bottom, what we will do is, we will take an element of small width dx. I have shown it large here, but this is a very, very, very small width dx. Okay, and we are drawing this dx width separately. Right. Now, suppose the tension here is T, then the tension here will be T plus dt, because at x, if the tension is T, then at x plus dx, the tension will be T plus dt. Okay. Now, only concentrate on this element. Forget everything. Only concentrate on this element. What will you write? We will write the stress. The stress is equal to Young's modulus into strain. This is Hooke's law. We will assume that the rod is completely elastic and it is in the elastic region. Okay, so the stress is that much that it has not crossed the elastic limit. We will not solve numericals in which the substance has so much stress that it has crossed the elastic limit. We will not do that. Okay, every time the body will be in its elastic limit. Okay, so if we concentrate on this element, then what we will assume here is, see, because the thickness is so small, we will assume that the tension here, which is mgx by L, is almost equal to the tension here, which is mgx plus dx by L. Okay, because dx is very small. So in this small element, we will assume that the tension is constant, and that is mgx by L. So here stress is force upon area. So mgx by L divided by the area of cross section is, suppose A, okay, is equal to y delta L by L. Now, what is the length? The length of this element. We have to only concentrate on this element. We are calculating the elongation of this element only. Forget everything. Only this element is the, means your body. Okay, so the length of this element is dx, delta L by original length, right? So original length of this element is dx, and dl is the elongation. dl is the elongation of the element. Okay, dl is the elongation of the element. All right, then mgx by La dx by y also is equal to integration dl. Okay, I have just separated the variables, and we have got integration dl is equal to mg by yal integration x dx. Now at x equal to 0, the tension is 0 and the elongation is 0. At x equal to L, the elongation is delta L. So the net elongation will be summation of the elongation of all the small elements, and that will be equal to delta L. Okay, so when you solve this is a very simple integration. You will see x dx integration is x square by 2, and when you put the limit, it will become L square by 2. So delta L is equal to mgl square by 2yal. LL cancel, you will get the elongation is equal to mgl by 2ay. Okay, what you can do here is again multiply by L and L, again multiply by L and L, okay, in the numerator as well as the denominator. Then area multiplied by length is volume. Area of cross section multiplied by the length is the volume. Okay, so in that case you can say that mass per unit volume is what? Mass per unit volume is density. So you can write the elongation as mgl by 2ay, but you can also write the elongation in terms of density, and that is rho g L square by 2y. Okay, m by al becomes density rho. So sometimes they will give you the density of the material of the rod. Okay, but there is one shortcut to remember. Okay, see, you can assume that this rod is a point mass which is placed at the center of mass. Okay, so this rod of mass m is a point mass which is placed at the center of mass, that is the center of the rod, and it is connected by a massless string of length L by 2. Okay, in that case what will you say is, in that case delta L is equal to, because this is a simple case where this tension at every point here will be same, and that will be equal to mg. So you know that delta L is equal to FL by AY. So here F is directly you will write mg. Okay, length is L by 2, area of cross section will be remaining same. Why? So you will see mgl by 2ay. You are getting the same answer that we were getting here when we integrated. Okay, but actual method is the integration method only, because the elongation of every small segment is different. Okay, but you consider this whole body as a point mass placed at its center of mass, and it is connected by a massless rod, then you will get the same answer. This is the shortcut. So suppose you have a question where you have a rod of mass m and length L, but there is also a block connected at the end of the rod of mass m. In that case, what will be the elongation? So what will be the elongation in this case? See, due to only this, the elongation will be FL by AY, and that will be MGL by AY, because this will produce a tension mg at every point, yeah, small mg. But due to this, we have already calculated the elongation of the rod due to its own weight, that is capital MGL by 2AY. So the total elongation of this rod will be due to this as well as due to this, and that will be equal to small mgl by AY plus capital MGL by 2AY. So the elongation of the rod due to its own weight, you can remember one more shortcut, you just have to divide by 2 in the denominator, that's it. So that means if this was the case where a rod is massless and mass m is kept here, in that case its elongation is mgl by AY. But when this is happening, when there is a rod of mass m and length L, then the elongation is half of it. Just divide by 2 with this answer. Okay, so you can remember it like this also, but still you must know the method of integration, because that is how you will understand or you will get the feel of it. Okay, then the next question is very important. Suppose you have two frustum shaped rods. Now what is frustum shaped rod? First, frustum means a half cone. That means you have a cone, but it is cut from like, okay, so if it is cut like this, in that case you will get like this. This is a frustum shaped rod. Okay, you can also call it a truncated cone. Okay, so a cone which is cut. Now they have given you two situations where the rod is kept like this, and then in the second situation the rod is kept like this. The upper radius is A and the below radius is B. Here the upper radius is B and the below radius is A. The rod is massless, but there is a mass M connected to both the rods. Okay, so the area of cross section in this case is varying, right? The length of both the rods obviously is same. Now they are asking you, will the elongation be same in the two rods? So what we will do here is, because the stress is different at different elements, so the strain is different, right? Strain is different means the elongation is different. That is why we have to take small elements and then find the elongation of this element and then integrate. Okay, so first we will do it for this one. Okay, so let at a distance x, let us take an element of width dx, and suppose the radius here is r. Okay, what we will do now is we will construct one triangle like this triangle here. Okay, at a distance x we have completed, means we have taken a width, we have taken an element of width dx. Okay, so now in this triangle you can see that this is similar to this, right? Now this length is a, this length is r, because this is a, this is also a. Okay, so this length is r minus a. Similarly, because this length is a, this length is b, so this length is b minus a, and this triangle is similar to this triangle. If these two triangles are similar, you know that in similar triangles the ratio of sides are same. So you will write r minus a divided by b minus a is equal to, this length is x and this length is l, is equal to x by l. Okay, so from this you will get the radius as a function of x. So because radius is different at every element, so the radius is a function of x. As x changes, the value of the radius changes. Okay, so once you get the value of the radius, that means you have got the area of the cross section. Okay, so now let us concentrate on this element, and the tension at every element is same, that is mg, because it is a massless rod. Okay, so the tension is mg divided by area is the stress, area is pi r square, is equal to y delta L by L. Now length of this element is dx and elongation is dl. Okay, again you will separate the variables and integrate, but for that, see here the variable is r, but you have to integrate it with respect to x. So that is why what we will do is we will replace this r with a plus b minus a by L into x. Let us say that this b minus a by L is lambda. Let us say that this b minus a by L is lambda. So if this b minus a by L is lambda, then you will write r is equal to a plus lambda x. Okay, so if here what we will do is we will replace r square with a plus lambda x whole square. Okay, so you will get mg by pi a plus lambda x whole square dx is equal to y dl. Again you will integrate from x equal to 0 to L, you will get the elongation delta L. Okay, now there is a shortcut to this, and this is very important. I'll tell you, you can treat this frustum to be a cylinder. You can think of this frustum as a cylinder of same length, and area of cross section, that is this one, as pi AB, pi into upper radius multiplied by lower radius. So you can treat this frustum as a cylinder of average area pi AB. In that case, the area of cross section become uniform and the elongation comes out to be delta L is equal to FL by AY. F is mg, L is length L, area is pi AB multiplied by the Young's modulus. So when you integrate this, you will get the same answer, and that will be equal to mgl by y pi b. Now let us look at this second case. In this case, what they have done is the lower end is shifted upwards, right? But still the shortcut will hold. That means you can treat this frustum as a cylinder of average area pi AB. So that means the elongation will come out to be same. So the question was, will the elongation be same in the above two rods of same geometry and same weight? Yes, the elongation will be same. Okay, now let us come to the next question. In this question, it is given that we have a ring of Young's modulus y, area of cross section a, the radius r, and mass m. And it suddenly starts to rotate with an angular velocity omega. So what they are asking you is, find the elongation in this rod when it starts to rotate with an angular velocity omega. Okay. So what we will do here is we will take a very small element on this ring which makes an angle 2 theta at the center. This theta is very small. Okay. We also know that the length of the arc is equal to r into theta, right? So if this angle is 2 theta, then the length of this arc is r into 2 theta. Okay. So the length of this arc is r multiplied by 2 theta. Okay. Now you know that tension is a pulling force, right? So if this is your system, then this part of the ring is pulling it towards itself. So this is the tension from this part, and this part of the ring is pulling the system towards itself. So there are two forces here, this one from this side and this tension from this side. Okay. When you look at this diagram, you will see if this angle is 2 theta, then this half angle is theta, right? So if this half angle is theta, this angle is also theta. Why? Because these two lines are parallel. Now this is radius and this is tangent and this is radius, and this angle is theta, this angle is 90 minus theta. If this angle is 90 minus theta, that means this angle is also theta. Same for this, if this angle is theta, this angle is also theta. Okay. So now if this is T, then this is T cos theta. Similarly, if this is tension, then this is also T cos theta. Now you can see from this diagram that T cos theta and T cos theta gets cancelled out, right? So the T cos theta component is cancelling out. Then this is T sin theta here. This was T, this is T cos theta, this is T sin theta. We have resolved this tension into two components. Similarly, if this is T cos theta and this is T sin theta. Okay, so the net force downwards is 2T sin theta. Now this element is so small, I have drawn it big, but actually this element is very small. So if this element is very small, that means you can treat this force, that is 2T sin theta, towards the center. So if this 2T sin theta is towards the center, that means this 2T sin theta force is responsible for the circular motion of the element. You know that for any particle which is performing a circular motion, there has to be a centripetal force, right? And this centripetal force here is provided by 2T sin theta for this particle. So 2T sin theta has to be equal to dm omega square r, where dm is the elemental mass of this element. Okay. Now dm, see, total mass is m, right? So total mass is m, then mass per unit length is m by 2 pi r, because the total length is 2 pi r. But the mass of this element is what? Mass per unit length multiplied by length, and this length is how much? R into 2 theta. So the mass of this element is m by 2 pi r into r into 2 theta. You can also use unitary method. What is that? 2 pi r length has m mass. 2 pi r length has m mass, then unit length has m by 2 pi r mass. And if unit length has m by 2 pi r mass, then what is the length of this? R into 2 theta. So r into 2 theta length has m by 2 pi r multiplied by r into 2 theta. Okay. So this is dm. This mass is dm. So dm into omega square r. So you know that any centripetal force is equal to m omega square r, right? So this is the centripetal force, and centripetal force is equal to m omega square r, where m is this dm, mass of the element. Okay. From this, sin theta can be written as theta. Why? Because theta is very small. This is a very small element. If this is a very small element, what you will say is that sin theta can be written as theta. Okay. So sin theta is replaced with theta. So here 2 theta and here 2 theta gets cancelled out. R also getting cancelled out. Okay. So you will say that the tension comes out to be m omega square r divided by 2 pi. So this is the tension in this, right? There was also one shortcut that you can use to find the tension in the ring. Okay. What is that shortcut? See, shortcut is tension in any ring is F outward on an element divided by 2 pi. I'll tell you. Suppose this is a ring. Okay. And just sit in this ring and sit on this element. This is a very small element. Just sit on this element. You know that if you sit on this element, then you will experience a centrifugal force. That will be the outward force. And what will be the centrifugal force? Dm omega square r. Okay, centrifugal force is what? The pseudo force which you experience when you sit on the frame of the circle. So this particle is performing circular motion. Sit in the frame of this particle, then you will say that there is a centrifugal force outwards, right? And that will be how much? Dm omega square r. Okay. Now tension, you can remember this formula, that tension in any ring is always equal to the outward force on this element divided by 2 pi. That's it. So it will be dm omega square r divided by 2 pi. Just what you have to do is replace this dm with total mass. When you replace this dm with total mass, you will get T is equal to m omega square r. Just replace dm with total mass. Okay, then you will get T is equal to m omega square r divided by 2 pi. So this is the tension that we have got here, and this is the tension that we got using the element method. Okay, but this is the shortcut. If you can remember, tension in ring is always equal to F outward upon. In fact, this is valid for half ring or quarter ring or an arc also. See, if you have an arc, I'll write it here. If you have an arc, then this is the arc and this angle is theta, then the tension in this arc will be equal to, suppose this arc is only rotating about this axis, then you will say that tension is equal to, again, m omega square r divided by, instead of 2 pi you will write theta. So you will say for an arc the tension is F outward divided by theta. For a complete ring, this theta becomes 2 pi. Okay. Now once you have the tension, you know that stress is equal to Y into strain, right? So stress will be how much? Tension per unit area. Then you will say tension is the external force. Yes, tension is the external force, but stress is restoring force per unit area. We are only considering elastic bodies. Completely elastic bodies always has restoring force which is equal to the deforming. So this T is the magnitude wise, it is equal to m omega square r by 2 pi, but actually this is the restoring force. Okay, so T by A is m omega square r divided by 2 pi divided by A. Okay, I have not put the value. You can put the value of T here. T by A is equal to Y delta L by L. Now what is delta L? Delta L is, so original length is 2 pi r and the change in length will be 2 pi delta r. So this is delta L, this is L. Okay, so 2 pi getting cancelled. From this you will get delta r is equal to TR by AY. Just put the value of T here, you will get the answer. Okay, in this case they can also ask you one more question, that is, find the maximum angular velocity, that can be given to a ring whose breaking stress is sigma. So that means what they are saying is the maximum stress that this ring can handle is sigma. Then what is the maximum velocity that we can give, or maximum angular velocity that we can give? Okay, so what we will do here is, this ring, suppose it is rotating with an angular velocity which is equal to omega max. Okay, in that case what we will say is, see, you know that T is equal to m omega max square r divided by 2 pi, because we know that tension in the ring is m omega square r divided by 2 pi. Okay, and suppose the area of cross section is A, then you will write T by A is equal to m omega max square r divided by 2 pi A. Now T by A is the maximum stress, that is sigma, it is given in the question. So you will write this as sigma 2 pi A divided by mr is equal to omega max square. Okay, so omega max will be root over this. But most of the time they ask you the answer in terms of density. Now, m by 2 pi r multiplied by the area of cross section. See, if you open this ring, it will become like this rod whose length is 2 pi r and the area of cross section is a. So in this case, what will you say? You will say that the volume is 2 pi r into a, right? So the volume of this ring element, means of this material of this ring, is 2 pi ra. So m by 2 pi ra is density. So what we will do here is, this can be written as root over sigma. We will multiply this by r and divide this by r. Then m divided by 2 pi ra is density. Okay, so you will write sigma divided by rho r square is equal to the maximum angular velocity that can be given to the ring so that it does not break. If you give angular velocity which is more than the maximum velocity, in that case the ring will break. Okay, so the angular velocity can be only up to that much, that it is not crossing the maximum stress that the ring can take. Okay, now let us look at the next question. You have a rod which is rotating about this axis with an angular velocity omega. The length of the rod is given. I will solve it in terms of variable, and this length is suppose L, and the area of the cross section of the rod is A. They have given you the radius, so from that you can calculate the area, that is pi r square. Okay, so area is pi r square. I'll write it in terms of area only. Afterwards, at the end of the, when you get the answer in terms of the variables, you can put the values to get the final result. Okay, we need to find the elongation in the rod as soon as it starts rotating with an angular velocity omega. So what you have to do here is, first we have to find tension at each point. So what we will do for that is, because the radius of every element is different, so definitely the tension will be different. So what I will do here is, at a distance x, first I will take an element of width dx. Okay, suppose the tension here is T, then the tension here is T plus dt. But you know that this element is performing circular motion, that means there has to be a centripetal force, and the centripetal force here is provided by the tension. So if I draw the FBD here, then you will see that there is a tension force here T, and you know that the tension is a pulling force, so this part will pull it towards itself and this part will pull it towards itself with T plus dt. Clearly here you can see that dt has to be negative. Why dt has to be negative? Because the net force has to be towards the center, that means T has to be more than T plus dt. That is possible only if dt is negative. So I will write like this, T minus T plus dt is equal to, this is the net force towards the center, this is the centripetal force. So this is equal to the centripetal force, and this has to be equal to dm omega square x. Why? Because you are only considering this element whose mass is dm, and this is performing circular motion with the help of the tension from the rod. Okay, so now you will write dt is equal to minus dm. Now what is dm? Dm is mass per unit length, multiplied by length, and this length is dx. Okay, so from this we will get T is equal to, now integration or putting the limits here is the trickiest part. See, we know that as x increases, tension is decreasing. Why? Because this dt is negative, that means the tension keeps on decreasing. So as x increases, tension decreases. Okay, that means tension is maximum at x equal to 0. Tension is maximum at x equal to 0 and 0 at x equal to L. At this point there is no body which is pulling this. Okay, so that means at this point the tension has to be 0. Okay, so the tension here is 0, that means at x equal to L the tension is 0. So what we will do here is dt is equal to minus m by L omega square x dx. I will integrate this and I will write at x equal to L the tension is 0. This is very important. See, at x equal to L the tension is 0. At x equal to 0 the tension is maximum, but we don't know the value yet. Okay, so the lower limit what I will put is x equal to L. At x equal to L the tension is 0. Okay, students make mistakes here when they write at x equal to 0 tension becomes 0. No, that is wrong. The tension is maximum in fact at x equal to 0. The tension is minimum at x equal to L. Okay, at the end of the rod the tension will be minimum and that is 0. Okay, and at the starting of the rod means what? That means the point where there is the axis. That point will have the maximum tension. Okay, so from here at any x, let us the tension be T. Then you will say T is equal to m omega square by 2 L, m omega square by 2L into L square minus x square. When you put the limits, you will get this answer. So you have now got the tension as a function of x. We have now got the tension as a function of x. Okay, but we need to find the elongation. We have just reached the tension now. So tension, you can see here, is a variable. Tension varies with x. If tension varies with x, in that case what you have to do is you have to take an element and you have to see the elongation of this element and then you have to integrate. So what I will do is, again I will draw this at x. Let us take a small element of width dx and concentrate on this element. Concentrate on this element. So if you concentrate on this element, then the length of this element is d. And if you apply Hooke's law on this element, you will write T. Now because this dx is so small, I will assume that the tension here is same, that is equal to the tension which was at the distance x. Okay, although this is x and this is x plus dx, so obviously the tension here will be Tx and here the tension will be Tx plus dx, but because dx is so small, I will assume that the tension in this element is constant, and that is m omega square by 2L into L square minus x square. So I will write m omega square by 2L into L square minus x square divided by area. This is the stress is equal to y multiplied by strain. Now again, writing the strain is tricky because we are just writing the strain on this element. So you have to say that the length is dx and the elongation on this dx element is suppose dl. So dl is the elongation of this element only. Okay, so from this again you will get m omega square by 2LA integration L square minus x square dx. Again y also I can bring it here only. You will get, now again at x equal to 0 to x equal to L, when you integrate you will get integration dl is delta L. Summation of all the elongations of small elements give you the total elongation. So from this we will get delta L is equal to m omega square by 2 y a L into L square x minus x cube by 3 integrated from 0 to. When you integrate this, you will get delta L is equal to m omega square divided by 2 yAl into L cube minus L cube by 3, that is 2L cube by 3. 2 cancel, you will get delta L is equal to m omega square L square divided by 3 YA. M omega square 1L getting cancelled, 1 2 got cancelled, you will get m omega square L square divided by 3 YA. But again, most of the time they ask you answer in terms of density. So you will write density is mass upon LA. LA is the volume because length multiplied by area of cross section is the volume. Okay, so from this you will get delta L is equal to m omega square L cube divided by 3 y LA. What I have done is I have multiplied the numerator and denominator with L again. Then AL becomes the volume and M by volume becomes the density. So you will say this is equal to density multiplied by omega square multiplied by L cube divided by 3y. Okay. So this is the elongation in terms of density. Okay. Now in the next question, they have given you a ring which is charged with a linear charge density lambda, and it is made up of a wire of cross section A and Young's modulus Y. Okay. Now what happens is a charge Q naught is placed at the center. As soon as the charge Q naught is placed at the center, they are asking you what is the elongation or what is the change in radius. Okay. Now this question is only for those students who are studying in class 12th and they have studied electrostatics. If you are in class 11 now, you can skip this question. Okay. So again I'll tell you the shortcut in any ring. This shortcut for ring is applicable every time. Okay. I will do this question only in terms of shortcut. So what I will do here is T, you know that T is equal to F outward upon 2 pi, right? T is equal to F outward upon 2 pi. Now let us take this small element. Okay. The charge on this element is dq. Now if the charge on this element is dq, then we will say T is equal to k q naught dq. Just replace dq by total charge, that's it. Replace dq by total charge. Okay, so I'll write integration dq, that is replace dq by total charge divided by r square, because every element is at a distance r, right? So every element is experiencing same force k q1 q2 by r square. Okay, whole divided by 2 pi, and integration dq will be lambda into 2 pi r because the charge density is lambda. So the tension will come out to be k q naught lambda into 2 pi r divided by r square divided by 2 pi. 2 pi cancel, 1 r also getting cancelled. So we will say tension is equal to k q naught lambda divided by r. Okay, once you get the tension, then again the same thing, you will say that T by A, that is the stress, is equal to Y delta R by R. You can also write 2 pi delta R by 2 pi R, but 2 pi will get cancelled anyways. So you will write delta R is equal to TR by AY. Just put the value of 2 here, you will get the change in radius. That is what is asked in this question. Okay, but suppose you don't want to use the shortcut, then what you have to do is again the same thing. You have to take the element here, and this side is pulling it with tension T, this is pulling with tension T, this angle we have taken 2 theta, the same thing that we have done in the question in which particle was rotating with angular velocity omega. The same thing you have to do here. This time the only thing is the tension is not the centripetal force, but this time the tension will be balanced by the electrostatic force. So you will write 2t sine theta is equal to k q naught dq by r square. That's it. You will get the same answer, this one. Okay. Now let us do a problem from IE Erodo 1.291. What internal pressure in the absence of an external pressure, that means there is no external pressure, which can be sustained by a glass tube and by a spherical glass flask if in both cases the wall thickness is of delta r, okay, and the radius of the tube and the flask is equal to r. The maximum stress that the material can handle is sigma b. That means sigma b is the breaking stress. Okay. So in this question what we will do is, see, first let us draw this cross section, this one. See, this will be the cross section. For the tube, this will be the cross section. And suppose the internal pressure is P, then you will say that the force on one side of the cylinder, force on one side of the cylinder is equal to the pressure multiplied by the projected area. We have discussed this in fluid mechanics. the force on one side of the cylinder will be equal to pressure multiplied by projected area. Pressure is same everywhere. Okay. So now this is equal to pressure multiplied by the projected area. Now this length is L, this length is 2r. Okay, it is actually 2r plus 2 delta r, but delta r can be neglected in front of r. So this length is 2r. So the area of projection, that is the projected area, will be equal to 2r multiplied by L. So this is the force on the cylinder, on one side of the cylinder, okay, or one side of the tube. Now this force will be balanced by the elastic force. So this force will be balanced by the elastic force, will be balanced by the elastic force. Now what is this elastic force? See, this thickness is delta r, right? So I'll draw the only the cross section now. The cross section delta r. So this is delta r and this is L, right? But like this there are two cross sections, okay, this one and this one. Okay. Now suppose the breaking stress is sigma. In that case the force here will be how much? Sigma into area. Now area this time will not be the area of the whole projected area. We will take only the area of the cross section of the material. That means you will take L multiplied by delta r. From here also L multiplied by delta r. That means 2L multiplied by delta r. So the elastic force will be equal to sigma multiplied by 2 delta r into L. But these two forces must balance each other. Okay, because it is in equilibrium, the net force has to be equal. Okay, so you will say that P into 2RL has to be equal to sigma into 2 delta RL. From this you will get 2L getting cancelled. You will get the maximum pressure that you can have is sigma delta R by R. If the pressure is more than this, then the cylinder will break. Why? Because in this case the pressure more means what? The outward force is more. Outward force is more. That means the elasticity of this material is unable to handle that much force. In that case the tube will burst. Now the second case is that you have a sphere. So when you have a sphere, in that case you know that for a sphere the projected area will be this pi r square. Okay, so this time the force due to pressure on one side of the cylinder, the net force is 0, but only I am taking the one side. Okay, so the force on the cylinder due to one side, force on one side of the cylinder due to pressure, force on one side of the cylinder, this time it's not cylinder, I'm so sorry, this is the sphere. So force on one side of the sphere is equal to pressure multiplied by the projected area, and this time the projected area is pi r square. But this time what will be the length? Length is 2 pi r, and just looking at the material thickness is delta r, right? The material thickness is delta r. So this force due to pressure is in this direction. At every point on the sphere it is in this direction. It is a three-dimensional. Every point on the sphere the force due to pressure is towards right, and the elastic force is trying to balance it. So the elastic force is in this direction. Okay, the elastic force is in this direction. So I will say that the elastic force will be sigma. Elastic force will be sigma. Sigma is the maximum stress. Okay, because we are asked to find the maximum pressure, so I am writing the maximum force that can be given by the elastic force. So sigma multiplied by area. Now what will be this area? This area will be 2 pi r multiplied by the thickness, that is. This two force has to balance each other. So we will say P pi r square is equal to sigma 2 pi r delta r. R getting cancelled, okay, pi getting cancelled. So you will say P is equal to 2 sigma delta r divided by r. So this is the maximum. In this question it is given that you have a rod of length 2L, okay, and the area of cross section of this rod is A, and the Young's modulus of the material of this rod is Y, and it is fixed or supported at its two ends with the help of wall. at the center a block is attached through a string, okay, and when you attach this block on this rod, what will happen is this this rod will bend, okay. So this rod will bend and you are asked find the descent in this rod, okay. Now in this triangle, suppose this angle is theta and this the descent is y. We need to find this y. If this length is L, from this triangle you can see that this length is L sec theta. Okay, so if this length is L, this length is L sec theta, then the elongation will be how much? See, initially the length was 2L, but now the length is L sec theta plus L sec theta, that is 2L sec theta. Sec theta is greater than 1. So the final length is 2L sec theta, the initial length is 2L. So the change in length, that is the elongation, is 2L sec theta minus 2L, that is 2L into sec theta minus 1. Now what is the strain? The strain is delta L by L, that is elongation by original length. Now original length was 2L, so the strain will be 2L into sec theta minus 1 divided by 2L, that is equal to sec theta minus 1. So we have got the value of the strain. Now, if you draw the FBD, then at this point, see at this point, there is tension T. Here also there is tension T and here there is gravity mg. Okay, so I've drawn it here. There is tension T, and here there is gravity. So for the equilibrium of this point, you will say that 2t sine theta has to be balanced by mg, because if this is t cos 90 minus theta, that is t sine theta. Okay, from here you will see that t cos theta and from here t cos theta is getting cancelled out. Only 2t sine theta is upwards and 2t sine theta will be balanced by the force of gravity at equilibrium. So I'll say 2t sine theta is equal to mg. So from this we will get T is equal to mg by 2 cosec theta. So we have got the value of the tension in the rod. Once you have got the value of the tension, you will get the value of stress. And you know by Hooke's law, stress is equal to y into strain. So you know that stress is equal to y into strain. So I'll write stress as tension, that is mg by 2 cosec theta divided by area. Area is given as A, is by into strain. Strain we have already calculated, it is sec theta minus 1. Okay, so from this you will get mg by 2a is equal mg by 2ay, also I can write mg by 2ay is equal to, now sec theta by cosec theta is tan theta. Okay, so you will write tan theta minus 1 by cosec theta is sin theta. Okay, now you know that this theta will be very small. Why? Because obviously due to this mass it will not descend by a very large angles. Okay, so we will take an assumption that this theta is very small. If theta is very small, in that case what we will do is you will write sin theta is nearly equal to theta. Okay, so we will say that here, see, tan theta is equal to y by L. See from here, tan theta, this is y, this is L, so tan theta is y by L. Okay, but sin theta is how much? Sin theta is y by under root, sin theta is how much? Y by under root L square plus y square. Okay, so sin theta is equal to y by under root L square plus y square. Now what I will do here is, see, sin theta is equal to y upon, I will take L square common. So if you take L square common, means root of L square will become L and you will get 1 plus y square by L square. From this you will get y by L into 1 plus y square by L square whole power minus half. Now because y is very small compared to L, so y by L is very small, right? Then y square by L square will be even smaller. Okay, so y by L is very small. So if y by L is very small, we can use this approximation, 1 plus x whole power n is nearly equal to 1 plus nx. So you will say sin theta is equal to y by L into 1 minus y square by 2. Okay, now once you've got this, sine theta minus tan theta from here, see, tan theta minus sine theta, sorry, tan theta minus sine theta will be how much? Tan theta minus sine theta is equal to y by L minus y by L into 1 minus y square by 2L square. From this we will get y by L cancel, you will get y cube by 2L cube. So this is the value of sine theta minus, sorry, tan theta minus sine theta. Now once you've got the value of tan theta minus sine theta, you know that this is equal to mg by 2ay. Now don't confuse with the small y and capital Y. Capital Y is the Young's modulus and small y is the descent. So you will write this as mg by 2 LAY from here. Okay, not L, sorry, there is no L. Mg by 2 AY. So from this you will get y cube is equal to 2 getting cancelled. Mg by AY. So from this you will get, take cube root, you will get y is equal to mg by AY whole power 1 by 3. So this is the descent. Okay, now you will ask me one thing, that here tan theta, because theta is small, so tan theta minus sine theta can be written as 0 because tan theta is also nearly equal to theta, sine theta is also nearly equal to theta. Never take an approximation up to an extent, never take an approximation up to an extent that the approximation gives you 0 value. No, you cannot take an approximation up to an extent when you get 0 value. See, there is a huge difference between 0 and 0.000000001. There is a huge difference. So you cannot take approximation up to an extent that you get 0 value. So that is why here I have not written sine theta as theta or tan theta as theta. Okay, I have written tan theta as y by L and sine theta as y by under root L square plus y square. Then I have used this one, this approximation. This 1 plus x whole power n is 1 plus nx. Okay, now in this question what they are asking you is, there is a rod of mass m and length L. Okay, it is on a frictionless surface and there are two forces acting on it, one is F1 and the other is F2. Suppose that F1 is greater than F2 so that this rod will move towards right. Suppose the area of cross section is A and the Young's modulus of the material of this rod is Y. Now by applying Newton's second law, you know that the net force on this is F1 minus F2. So you will write F1 minus F2 is equal to mass into acceleration. So from this you will get the acceleration of the rod as F1 minus F2 by m. We need to find the elongation of this rod. Okay, so here the rod is not fixed from any end, but still it will elongate. Both the forces are tensile. You can see that this also wants to stretch the rod and this also wants to stretch the rod. So both the forces are tensile. That means the rod will elongate. Okay, if the force would have been in this direction, in that case you would have said that the force is compressive. Both the forces are compressive. In that case the rod would have shortened. Okay, but in this case the rod will elongate. So first we have found out the acceleration. Now suppose we want to find the tension at any point, suppose this point P, okay, at a distance x. Now we know that we have studied in Newton's law that if you want to find a tension at that point, you have to take a system or you have to draw an FBD which has the boundary as that point. Okay, so let us take this system, okay, where P is the boundary. In that case you will say that, so this is the system and this mass is, see, L length has mass m, unit length has mass m by L, but this length is how much? If this is x, this length is L minus x. So L minus x length has mass m by L into L minus x. So we now have the mass of our FBD system, m by L into L minus x. Here the force acting is F1 and here the tension is T. Okay, tension is a pulling force and this part is getting pulled by this. Okay, so here F1 minus T will be equal to m by L into L minus x into A, because every part of this means of this rod is moving with the same acceleration a, and a is this. So you will write F1 minus t is equal to m by L into L minus x into F1 minus F2 divided by m. M getting cancelled. From here you will get t is equal to F1 minus F2 into L minus x by L. So you have got the value of t now. Once you have got the value of t, see t is a function of x. So at every point tension is different. If at every point tension is different, that means stress is different. Stress is different, that means strain is different, that means elongation is different. So if elongation is different at every point, what you have to do, you have to take an element and integrate. So what we will do again is, this is the rod. At a distance x, we will take an element of width dx and we will concentrate only on this element for now. So you will say that this element has a tension this, okay, because the thickness is so small, we will assume that the tension here at every point is same. Why? Because dx is very small, okay. So the tension at x is equal to the tension at x plus dx, because dx is very small, right? So you know that stress is equal to y strain, so I'll write T by A is equal to y delta L by L. The tension here will be this one, F1 minus F2 into L minus x by L divided by A is equal to see y multiplied by delta L. Delta L means the elongation of this element, okay. We will write it with dl, and what is length of this element is dx. We are concentrating only in this element, okay. So from this you will get f1 minus f2 by L into L minus x dx by ay, and write 1 by ay outside, is equal to integration d. So when you solve this, you will get the elongation delta L is equal to, you will integrate it from x equal to 0 to x equal to L. So the elongation, that is integration dl, will come out to be, see, f1 plus f2 into L divided by 2ay. Okay, I'll tell you a shortcut to remember this. See, you know that, listen carefully, you know that in general elongation is fl by ay. So elongation has to be of this form, okay. Now, whenever the tension is variable, and it is varying with x, okay, linear variation is there. See here, this one, tension is varying linearly. There is a linear variation of tension, okay. If there is a stress which varies linearly, in that case the denominator will have a term 2. Okay, and in this case, see, there are two forces which are trying to stretch the body, right? So the net force which is trying to stretch the body is F1 plus F2. You will say that these two are in opposite direction, so it should be F1 minus F2. No, both are trying to stretch. In FBD we have written F1 minus F2 only, but in the final answer both will try to elongate this rod, okay. So the elongation will be of this form always. F here is net force which is trying to stretch, so it is F1 plus F2, okay. L by ay, only the thing is the denominator is 2. Every time whenever the stress is linearly varying with x, you will say that the elongation will have a term 2 in the denominator every time. In fact, if tension or stress varies with x square, then here there will be 3. But here obviously it is not 3, because tension is, or stress is, varying with linearly with x, okay. But if stress is varying as a function of x square, then here it will be 3. For example, this case, if you remember, in this case the tension at a distance x was m omega square by 2l into L square minus x square. In this case the tension was varying with x square, that means stress was varying with x square. In that case, if you remember, the answer came out was, see, listen carefully, answer is always of this form, fl by ay. So here the answer came out was f is the tension, so I'll write m omega square L square. Okay, m omega square L square divided by ay, but you will add a 3 here. So if you remember, in that case we have written like this only, m omega square L, sorry, it was m omega square L, force is m omega square L multiplied by L. Force is m omega square L multiplied by L. So it came out m omega square L square divided by 3ay. You can go back on this video and you can check where we have solved this problem. You have got the same answer. Okay. If you remember, in case of elongation of a rod due to its own weight, here also tension was varying as a function of x. If tension was varying linearly with x, again if you remember, the answer was mgl fl by ay. There was 1 2, because whenever there is linear variation, the answer you will get a denominator term 2. Okay. With this, we come to the end of today's class. In this class, we practice different problems related to Young's modulus, that is the relation stress is equal to Y strain. In the next class, we will do some more problems. We will also discuss the elastic potential energy, and we will also do some problems related to bulk modulus. So stay tuned for my next video. Hello students, if you like my work, do hit the like button and share my work with your friends. Also, please subscribe to my channel and hit the bell icon. You'll be notified when I upload my next video.